My name is Viet. I'm from the University of Stuttgart, and I will present this work on behalf of my co-authors Sven and Niels Henze, who is from the University of Regensburg. So smartphones offer a wide range of functions which we can access through a touchscreen. And on a technical basis, touchscreens translate touches into two-dimensional coordinates which are mapped to the user interface. And this concept enables an intuitive interaction, but also limits the input expressiveness to a single two-dimensional coordinate. This limitation makes it challenging to provide shortcuts and secondary actions, which are actually fundamental on desktop and laptop computers. So to improve the input expressiveness, previous work explored the concept of finger-aware interaction on touchscreens. So basically, the touchscreen recognizes which finger is touching it to assign unique functions to each finger. So for example, the right thumb can be used to select objects, while the left thumb could be used to open a context menu, similar to how we use a computer mouse nowadays. So previous work presented a wide range of approaches to identify fingers for touch interaction. So one approach includes wearable sensors, which are attached to the user's fingers and hand. So the image here on the right shows a prototype by Masson et al., who used vibration sensors to identify the touching finger. But the major disadvantage of this approach is that it is inconvenient, since users have to deal with multiple sensors and devices. And another approach includes external cameras, which are attached to the touch device. So for example, Colli et al. Used a leap motion camera attached to the tablet to identify which finger touched it. But similar to the wearable sensors, this approach reduces the mobility, since the additional camera increases the bulkiness of the touch device. So instead of using external sensors, some touch sensing technologies provide a high-resolution touch image. So the image here on the right shows an example for touch sensors, which is based on frustrated total internal reflection. So basically, with such an image, computer vision-based approaches could determine the position of each finger, for example, with template matching. However, these sensors are not available for smaller mobile devices because of their size and also because of their immobile setup. So in contrast to these approaches, we use the raw measurements of capacitive touchscreens to identify fingers such as the left and the right thumb. So a visualization of these measurements is often referred to as a capacitive image and basically looks like this. So a capacitive image is a low-resolution fingerprint of the touch and is available on all mobile devices that feature a mutual capacitive touchscreen. So the Nexus 5 is often used as a reference device in literature and provides basically a 27 by 15 pixels image on a 5-inch screen. And despite the low resolution, previous work successfully used them for a wide range of use cases. For example, to recognize body parts or the palm for interaction, and also to estimate the finger orientation on a touchscreen. And closest to our work, Jill et al. Used capacitive images of smartwatches to identify the thumb, the index finger, and the middle finger. However, they assumed exaggerated finger poses, which is uncommon on smartphones, and also they showed that the identification of fingers in normal poses is not really feasible with a usable accuracy. So while previous work showed that identifying all fingers is not feasible because of the low resolution, the majority of the fingers are on the back of the device anyways to hold it while using the phone. And therefore, we argue that reliably differentiating between the main input finger and any other finger already extends the input vocabulary notably. So the main input finger, such as the right thumb, could be used for main actions, while the left thumb could activate secondary actions or shortcuts, similar to how we use a computer mouse. And therefore, the goal of this work is to find combinations of fingers that include the main input finger and any other finger that can be differentiated with a usable accuracy. So we follow 4 steps to find finger combinations that are usable. So first, we collect a representative data set of touches by all fingers. And we also share this data set with the community to enable them to do further investigations. In a second step, we then explore the data set to find distinctive features that help us to understand the differences between all the fingers. And in the third step, we then develop models that identify fingers and further validate them with a test set in the same step. And finally, we evaluate our best model in a user study with new participants. So besides the validation of the accuracy, this enables us to study the perceived usability of the model, how users adapt to it, how they use it, and to collect qualitative feedback on the use cases that we built upon our models. So we conducted a study to collect touches of all fingers on a Nexus 5 device. So as we can see in the video here on the right, we developed an application that instructs participants to perform different tasks which they solve with all their fingers. So our applications record all capacitive images in the background and label them with the fingers that the participant is supposed to use. And our study design includes two independent variables, the finger and the task, which includes a tapping task, a scrolling, and a dragging task. And these tasks were adopted from previous work and were repeated 30 times for each finger. And for this study, we recruited 20 participants. So after we collected our data set, we first removed all capacitive images which were empty or include multiple touches to avoid wrong labeling. And we further performed the blob detection to train a position-invariant model so that fingers can be identified everywhere on the screen. So in total, we have over 455,000 capacitive images that we can now use for exploration and to develop the model. So first, we overlaid all touch blobs for each finger to explore visual distinctive features. So the ellipses here on the images represent the mean size of the touch area, while the whiskers represent their standard deviation. And as a first step to model development, we start with using basic machine learning algorithms. So we followed the approach by previous work and used the ellipse properties as features to train random forests. So the green bars here represent the accuracies that we achieved with a random forest. And in comparison, the blue bars represent the baseline accuracy when always predicting the most occurring class. So we show the accuracies for the 4 best finger combinations that we found and for the model that identifies all 10 fingers. And if you're interested in the other results, please read the paper. So here, the best performing model is just below 80% in accuracy, which is a good start, but we can still do better. So deep learning models such as convolutional neural networks take the raw image pixels as input and are much more successful here. So the yellow bars show the accuracies of these CNNs, which all outperform the random forests. And interestingly, the model for differentiating between left and right thumb achieved an accuracy of over 90% on the test set. And other models, such as the model for thumb and index or thumb versus others, achieved a slightly lower accuracy at 84 to 86% on the test set. However, the identification of all 10 fingers achieved an accuracy of 36%, which is not usable. So we went a step further and looked into more specific models. So in a real system, only the first tap is relevant since the finger cannot change until it is lifted up from the display. So the orange bar here shows the accuracy of the CNN, which was trained and tested only with the tapping data. So for the left-right thumb model, it increased the accuracy by 3%, which is now at 93%. But for our other models, the accuracy improved or decreased slightly. And we also trained models for each user independently. So in a real system, this would work similar to how fingerprint scanners on smartphones work nowadays. So they first collect the data and then identify the user based on it. So training models per user did not improve the left-right thumb model, but there are notable improvements, especially for the index finger model and also the 10-finger model, which is now at 86%. So since the model that differentiates the left and the right thumb performed the best out of all, we will focus on this one in the following. So the CNN that we trained for the left-right thumb model expects a 27:15 capacitive image as an input, and this is passed through 2 convolution layers with 64 filters, a 2x2 max pooling layer, and again, 2 convolution layers with 128 filters, followed by a 2x2 max pooling layer. And at the end, we have a dense layer with 256 neurons and an output of 2 neurons for each of the thumb. And to find the hyperparameters that performed the best on the test set, we performed a grid search as it was proposed in previous work. So we exported our CNN for the left-right thumb model and deployed it on a Nexus 5 using TensorFlow Mobile. So a classification on this device takes 19.2 milliseconds on average, so that it can run in the background and classify all touches. And with optimizations in phones nowadays, the classification time is basically neglectable. So based on the model, we developed 2 sample use cases. So the first use case represents a porous use interface, in which 2 applications are basically overlaid. So the idea is the right thumb interacts with the foreground application and the left thumb interacts with the background application. And in this example, we demonstrated this with a scrolling task as a background and a a scrolling task in the background and a dragging task in the foreground application. And this concept enables to use two applications simultaneously without switching between them. So the second use case is a painting application. So basically, users can draw with their thumb and open a context with the right thumb and open a context menu with the left thumb to switch the color and basically save space in the user interface. So after we developed the model and implemented sample use cases, we evaluated both in a user study. So basically, the study is necessary to validate the accuracy with new participants, to evaluate the perceived usability of the model, which is not reflected by the accuracy metric, and also to understand how users adapt to it and use it. And we also collected qualitative feedback on our sample use cases. And for this study, we recruited 10 participants who did not participate in the previous study. So the study consists of 3 parts. So in the first part, we used the exact same tasks as in the data collection study to collect a validation set. And this set enables us to validate the model accuracy with data from users which were neither involved in the training nor in the testing process. And in the second part of the study, participants use our porous user interface in which they solved a dragging task with the left thumb and a scrolling task with the right thumb. And our implementation used the model so that any classification error is directly visible to the user so that we can evaluate their reaction. And we evaluated the effective accuracy of the porous user interface, including the model as well as the human error. So basically, a human error occurred when the users used the wrong thumb for a given task. And in the last part of the study, participants used our painting application in which they could draw with the right thumb and color menu for color switching with the left thumb. So we first explained the application to the participants and then instructed them to draw an image of their last vacation as the task here. And they have used, and after they used the application, we conducted a semi-structured interview to collect their qualitative feedback on our use cases. So the first part of the study shows that the model is generalizing well and does not overfit to the 20 participants of the first study. And the accuracy with the validation set here is 92% compared to the 93% with the test set. And the second part shows the effective accuracy including model and human error in the porous user interface. So the mean effective accuracy here is 85.2%, while all users gave positive feedback on the use case and also perceived the learning process as easy. So after the participants used the porous interface and the painting application, they all responded that it is useful and easy to use. And for example, here P1 emphasized the usefulness of using 2 thumbs simultaneously, while P16 told us that he is already used to using both thumbs, which makes learning this method even easier. And also P5 found that the recognition was already very good, but that there were only 2 cases in which her finger was wrongly identified. So to sum up this talk, we investigated the feasibility of finger identification on capacitive touchscreens using deep learning. So first, we collected a data set and developed models to differentiate between different combinations of fingers. And one highlight is our position-invariant model that differentiates the right thumb from the left thumb with an accuracy of 93%. And based on this model, we implemented porous user interfaces and finger-aware shortcuts, which our participants found useful and intuitive. So in this work, we showed working and usable models for finger identification on a commodity smartphone, but this is just the start. So for feature work, we published our dataset on GitHub for further investigations. The accuracy, for example, could be improved with more specialized models like LSTMs that consider the touch trajectory for the classification. And we could also combine the capacitive images with further data, such as the position of a touch or even the data from the built-in IMU. And the finger identification could be further improved by using a touch sensor with a higher touch sensing resolution. So thank you for your attention, and I'm happy to take questions now.
Let's thank the speaker. Are there any questions? Well, I have one. Because you say, well, consider multiple data sources, have you also thought of using something that is multimodal? Let's say, you could imagine combining this with voice even, right, or other modalities?
Yeah, so this is definitely a good idea. So what we wanted to do in this work is just to show the feasibility of using the capacitive images to identify fingers. And sure, future work could combine the capacitive images with a lot of other data sources, like you said, voice, or the IMU, for example, and also how users move their fingers, which side it is. So there's a lot of information that could be included in the classification to improve the accuracy.
Okay, thank you. Any more questions? If not, it's time for the coffee break. Okay, so then we are closing the session. Let's thank the speaker again.